For centuries, humanity has pondered the nature of the cosmos, often envisioning space as a vast, empty void, a mere backdrop against which stars and galaxies perform their cosmic dance. Early astronomers, peering through rudimentary telescopes, saw only blackness punctuated by distant points of light, reinforcing this perception of an inert, passive canvas. This classical view suggested that the universe was primarily composed of matter, with space simply being the absence of it, a stage rather than an active participant in the grand cosmic narrative. Yet, as our understanding deepened, propelled by revolutionary scientific discoveries, this simple notion of emptiness began to unravel. The universe, it turns out, is far more intricate and dynamic than our initial observations suggested. The very fabric of space, once considered inert, has revealed itself to be a complex, energetic entity capable of influencing everything within it, from the smallest particles to the largest cosmic structures. To comprehend this transformation in our understanding, we must first establish what we mean by energy. In its most fundamental sense, energy is the capacity to do work, to cause change. It manifests in countless forms: the kinetic energy of motion, the potential energy stored in an object's position, the thermal energy of heat, the electromagnetic energy of light, and the nuclear energy binding atomic nuclei together. Each form plays a crucial role in shaping our perceived reality. In classical physics, dating back to Sir Isaac Newton, space was conceived as an absolute, unchanging arena where events unfolded, independent of the matter and forces within it. Time also flowed uniformly, separate from space. This framework provided an extraordinarily successful model for planetary motion and everyday mechanics, solidifying the idea of space as a static, infinite container. However, towards the end of the 19th century, anomalies began to emerge, challenging the classical paradigm. Experiments concerning the speed of light, particularly the Michelson-Morley experiment, suggested that light traveled at a constant speed regardless of the observer's motion, an observation that clashed directly with Newtonian physics. This hinted at a deeper, more profound connection between space, time, and motion. It was Albert Einstein, in his theories of special and general relativity, who utterly revolutionized our understanding. He proposed that space and time are not separate entities but are interwoven into a single, four-dimensional fabric called spacetime. This fabric is not merely a stage. It is an active participant, capable of being warped and curved by the presence of mass and energy. Albert Einstein's famous equation, E=mc², perhaps the most recognized equation in history, fundamentally linked energy and mass. It states that mass and energy are interchangeable. Mass can be converted into energy, and energy into mass. This equation revealed that even a tiny amount of mass contains an enormous amount of energy, fundamentally challenging the classical distinction between the two. The profound realization implied that the universe's matter content is, in essence, a crystallized form of energy. When we look at a star, a planet, or even ourselves, we are observing concentrations of energy that have taken on a material form. This blurs the lines between what was once considered empty space and the energetic components within it. Given that matter is a form of energy, what then of the space between these material concentrations? Is it truly empty, devoid of any energy signature? The Newtonian void couldn't account for the constant speed of light, and the concept of an ether, a hypothetical medium through which light propagated, was eventually disproven by experiment. The answer lay in a far more subtle and complex understanding. The true emptiness, a perfect vacuum with absolutely nothing in it, including particles, fields, or even energy, is perhaps a theoretical ideal that doesn't exist anywhere in the universe. Even in the deepest interstellar space, far from stars and galaxies, there are stray particles, electromagnetic fields, and the faint whisper of the cosmic microwave background radiation. The transition from classical concepts to modern physics began to reveal space as a dynamic arena, not a passive stage. This shift was monumental, moving from a universe where space was just a container to one where space itself had properties, could be distorted, and was intrinsically linked to its energetic contents. This new understanding necessitated a re-evaluation of energy itself. Beyond the familiar forms, scientists began to conceptualize energy as an inherent property of the quantum vacuum, an idea vastly different from the classical view of an energyless void. The implications were profound, suggesting that even nothingness possesses an energetic character. One of the earliest hints that space was not truly empty came from the concept of electromagnetic fields. Light, radio waves, and all forms of electromagnetic radiation are oscillations of these fields, which permeate all space. Even in the absence of charged particles, these fields exist, carrying energy and information across vast cosmic distances. These fields themselves possess energy. An electric field stores potential energy, and a magnetic field transports energy through space, as exemplified by the sun's energy reaching Earth. So even before the advent of quantum mechanics, the very concept of fields hinted at an energetic presence within the seemingly empty expanse of the cosmos. Therefore, the classical vacuum, a space completely devoid of anything, stood in stark contrast to the emerging view of a universe infused with fundamental fields. The idea that space could contain energy, even without observable matter, set the stage for one of the most revolutionary discoveries of the 20th century, the quantum mechanical description of reality. With the dawn of quantum mechanics in the early 20th century, our perception of reality took an even more radical turn. The quantum realm describes the behavior of matter and energy at the atomic and subatomic levels, revealing a universe far stranger and more dynamic than previously imagined. Here, particles behave as both waves and particles, and uncertainty is a fundamental principle. Within this quantum framework, the vacuum is not truly empty. Instead, it is a bustling arena of activity, teeming with what are known as quantum fluctuations. These are transient, spontaneous appearances and disappearances of particles and antiparticles out of seemingly empty space, governed by the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that we cannot simultaneously know with perfect precision certain pairs of properties, such as a particle's position and momentum, or its energy and the duration for which that energy exists. This implies that energy can spontaneously appear for a brief moment, as long as it disappears quickly enough to evade detection and satisfy the principle. These ephemeral particles, known as virtual particles, exist for fleeting moments before annihilating back into pure energy. They are not entirely real in the sense of stable, observable particles, but their effects are demonstrably real and measurable, profoundly impacting the properties of what we once considered an empty vacuum. One of the most compelling pieces of evidence for the energetic vacuum is the Casimir effect. Predicted in 1948 by Dutch physicist Hendrik Casimir, this phenomenon demonstrates that two uncharged, parallel conductive plates placed very close together in a vacuum will experience a small but measurable attractive force. This attractive force arises because the vacuum between the plates constrains the allowed wavelengths of virtual particles, reducing the number of virtual particles that can exist in that region compared to the space outside the plates. The imbalance in virtual particle pressure pushes the plates together, a direct manifestation of vacuum energy. The Casimir effect is not merely theoretical. It has been experimentally verified with remarkable precision. This verifiable force, literally pushing objects together from what should be empty space, provided concrete evidence that the vacuum possesses an intrinsic, energetic nature, challenging the very core of classical physics. This leads us to the concept of zero-point energy. In quantum mechanics, even at absolute zero temperature, where all classical motion ceases, a system still retains a minimum amount of energy due to these quantum fluctuations. This irreducible energy is the zero-point energy, inherent to all quantum fields, including the vacuum itself. So what does empty space truly mean in quantum terms? It's not empty at all. It's a vibrant, seething sea of potential energy, a cosmic ocean of virtual particles constantly popping into and out of existence. This quantum foam is the fundamental substratum of reality, underlying everything we perceive. The relationship between energy and matter is further illuminated by processes like pair production and annihilation. When a high-energy photon, a packet of pure energy, passes near a heavy nucleus, it can instantaneously convert into a particle-antiparticle pair, such as an electron and a positron. This is energy becoming matter. Conversely, when a particle meets its antiparticle counterpart, for example, an electron encountering a positron, they annihilate, converting their entire mass back into pure energy, usually in the form of photons. This constant dance of creation and destruction reinforces Albert Einstein's mass-energy equivalence. This dynamic interplay implies that matter is not something entirely separate from energy, but rather another manifestation of it, a localized concentration of energy bound together in a stable form. The cosmos is a continuous theater of these transformations. Therefore, the quantum vacuum represents the baseline energy state of the universe. It's not a true zero, but rather an energetic minimum from which all other energy differences are measured. This inherent energy of space itself has profound implications for cosmology, dictating the very fate of our universe. The idea that the vacuum is not empty provided the initial seeds for understanding some of the most perplexing cosmic phenomena. It paved the way for theories that would ultimately explain why the universe is not just expanding, but why that expansion is accelerating. The quantum realm whispers secrets of the cosmos at large. This fundamental energy of the vacuum, confirmed by quantum mechanics and experiments like the Casimir effect, establishes space as far from passive. It is a substratum teeming with energetic potential, a concept that would become critical when scientists began to probe the largest scales of the universe and its overall expansion. For much of the 20th century, astronomers observed that the universe was expanding. This profound discovery, largely credited to Edwin Hubble, showed that galaxies are generally moving away from us, and the farther away they are, the faster they recede. This unequivocally established that the universe is not static. Initially, it was assumed that this expansion would either slow down over time, due to the gravitational pull of all the matter within the universe, or it would eventually contract in a big crunch. Gravity, after all, is an attractive force, so it should act to break the expansion. However, in the late 1990s, two independent teams of astronomers studying distant supernovae made a truly astonishing discovery. The universe's expansion is not slowing down. It is accelerating. This was a monumental shock, turning established cosmological theories on their head. To explain this phenomenon, cosmologists posited the existence of a mysterious, repulsive force counteracting gravity, pushing galaxies apart at an ever-increasing rate. This enigmatic entity was dubbed dark energy, and it utterly transformed our understanding of the cosmos. Dark energy is unlike anything we have ever directly observed or understood. It's not like matter or dark matter, which clumps together. Instead, dark energy appears to be spread uniformly throughout space, an intrinsic property of the vacuum itself, exerting a constant outward pressure. The magnitude of dark energy's influence is staggering. Current cosmological models suggest that dark energy accounts for approximately 68% of the total energy density of the universe. This means that the majority of our universe is actually made up of this mysterious, invisible force. One leading candidate for dark energy is the cosmological constant, a term Albert Einstein originally introduced into his field, equations of general relativity. He used it to allow for a static universe, which he later called his biggest blunder after Edwin Hubble discovered the universe was expanding. Ironically, Albert Einstein's biggest blunder has been resurrected. If the cosmological constant represents the energy density of the vacuum that remains constant as space expands, it perfectly explains the accelerating expansion. This would mean that pure, empty space intrinsically contains energy. The cosmological constant implies that as the universe expands, more empty space is created, and with it, more dark energy. This means the overall amount of dark energy increases with the volume of the universe, and it drives an even faster acceleration, creating a self-reinforcing expansion. So, is dark energy the same as the quantum vacuum energy we discussed earlier? This is a profound and active area of research. While both relate to the energy of empty space, there's a colossal discrepancy. Theoretical calculations of vacuum energy from quantum mechanics predict a value vastly, astronomically larger than the observed dark energy. This cosmological constant problem is one of the biggest unsolved mysteries in theoretical physics, a monumental mismatch between prediction and observation. It indicates either a profound misunderstanding of quantum gravity, or that dark energy is not simply the quantum vacuum energy after all, but something else entirely. Regardless of its precise origin, dark energy provides a compelling answer to our core question. If space has an intrinsic uniform property that causes it to expand, then space is demonstrably energetic. It is not merely a stage, but a dynamic, self-propelling agent of cosmic evolution. Dark energy's existence fundamentally changes our picture of the universe's ultimate fate. Instead of a big crunch, or even a gradual slowing, the accelerating expansion points towards a future where galaxies beyond our local group will eventually recede so fast they will become forever invisible, leading to a cold, dark, and empty universe. This expansion means that the very scale of the universe itself is evolving, not just the objects within it. The metric of space-time is stretching, carrying everything along with it, and this stretching is powered by an inherent energy associated with space. So the answer to whether space is pure energy is becoming increasingly clear. While not pure in the sense of only energy, it undeniably possesses energetic properties. It is permeated by quantum vacuum energy, and on the largest scales, dominated by dark energy, which dictates its accelerating expansion. To further understand the energetic nature of space, we must delve deeper into Albert Einstein's masterpiece, the theory of general relativity. This revolutionary framework doesn't just see space and time as separate entities, but as a unified, flexible fabric known as space-time. General relativity posits that gravity is not a force pulling objects together, as Sir Isaac Newton described. Instead, gravity is the manifestation of the curvature of space-time caused by the presence of mass and energy. Massive objects warp the fabric of space-time around them, and other objects simply follow these curves, creating the illusion of a gravitational pull. This means that matter and energy dictate the geometry of space-time, and in turn, the geometry of space-time dictates how matter and energy move. It's a dynamic, interactive relationship, fundamentally linking the energetic content of the universe to its very geometry. Every bit of mass and every form of energy contributes to this warping. A star's immense gravity is a profound curvature. Even the energy of a light beam, though massless, contributes to the local energy density and therefore influences the space-time around it, albeit to a tiny extent. This concept means that space is not just filled with energy. Space is energy, in a sense, as its very structure and dynamics are determined by its energetic content. The geometry of space itself becomes an energetic field. The effects of space-time curvature are not just theoretical, they are exquisitely confirmed by observation. From the precise orbits of planets to the bending of starlight around massive galaxies, and even the slight time dilation experienced by GPS satellites, general relativity consistently passes rigorous tests. One of the most spectacular predictions of general relativity was the existence of gravitational waves. These are ripples in the fabric of space-time itself, generated by accelerating massive objects, like colliding black holes or neutron stars. When these gravitational waves pass through us, they momentarily stretch and squeeze space itself. This stretching and squeezing is a direct manifestation of energy propagating through the fabric of space-time, carrying information about the cataclysmic events that created them. The direct detection of gravitational waves starting in 2015 by the LIGO and Virgo observatories marked a new era in astronomy and provided yet another powerful confirmation that space-time is a dynamic, energetic entity, not a static void. These ripples are energy in motion through space-time. Black holes represent the most extreme warping of space-time imaginable. Their immense gravity creates a point of no return called the event horizon, where space-time is so severely curved that nothing, not even light, can escape. Their very existence is a testament to the dynamic interplay of mass, energy, and space. The singularity at the heart of a black hole, where space-time curvature is infinite, is a point of extreme energy density. It's a place where our current understanding of physics breaks down, suggesting that space, energy, and matter are woven together in ways we are still struggling to comprehend fully. The universe's energy budget is a complex accounting. Visible matter, the stars, planets, and gas clouds we can see, constitutes a mere 5% of the total energy density. The vast majority is unseen, unknown, and profoundly influential. The fact that gravity itself is a manifestation of the energetic curvature of space-time leads to a powerful conclusion. Space is not merely filled with energy, but its very geometry embodies and conveys energy. The shape of space is a form of energy. Even with the presence of dark energy, the interplay with matter and energy is continuous. The expansion driven by dark energy stretches space, reducing the density of matter and radiation, further changing the geometry and enabling dark energy to become even more dominant over time. General relativity eloquently demonstrates that space is not just a stage for energy, but an active, energetic component of the universe itself. Understanding its curvature, its dynamic nature, and its responsiveness to matter and energy is key to unraveling the cosmos's deepest secrets. Let's consider the universe's full energy composition, a cosmic census that has profoundly reshaped our understanding of reality. This census reveals that the universe is far from being dominated by what we can see or directly interact with. Visible matter, sometimes referred to as baryonic matter, is the stuff that makes up everything from atoms to stars, galaxies, and ourselves. This familiar matter accounts for only about 4.9% of the universe's total mass energy density. It's a surprisingly tiny fraction of the whole. Dominating the missing mass of the universe is dark matter, a mysterious substance that does not emit, absorb, or reflect light and interacts very weakly with ordinary matter. We detect its presence only through its gravitational effects on galaxies and galaxy clusters. It makes up approximately 26.8% of the universe. Dark matter forms the invisible scaffolding upon which the visible universe is built. Without its gravitational influence, galaxies would fly apart, and cosmic structures wouldn't hold together. It's a form of matter, but its true nature remains one of the greatest puzzles in physics. However, the most dominant component, by far, is dark energy, which we've learned is responsible for the accelerating expansion of the universe. It accounts for an astounding 68.3% of the total energy content. This means the vast majority of our universe is not matter, but this mysterious energy permeating space itself. This cosmic inventory reveals a profound truth. What we perceive as space is not just the absence of visible matter, but is predominantly filled with energetic components that dictate its geometry and evolution. The concept of pure emptiness is increasingly untenable. The constant energy density of dark energy means that as the universe expands and its volume increases, the total amount of dark energy also increases proportionally. This self-amplifying effect strengthens its influence over time, ensuring continued acceleration. The cosmic microwave background, or CMB, is a faint glow of radiation left over from the Big Bang. It provides a baby picture of the universe, revealing tiny temperature fluctuations that encode information about the universe's composition and geometry when it was only about 380,000 years old. Analysis of the CMB, particularly its anisotropies, confirmed the flat geometry of the universe and supported the existence and proportions of dark energy and dark matter. It's an observational triumph that underpins our modern cosmological model. This flat geometry, meaning the universe's overall shape is not curved like a sphere or a saddle, implies that the total energy density of the universe must be equal to a specific critical density. Dark energy is essential to make up the missing portion required for this observed flatness. Without dark energy, the universe would either have long ago collapsed back on itself or expanded much slower, leading to a different fate and a different cosmic evolution. Its presence is vital for the universe as we observe it today. The early universe was dominated by radiation and then matter. As the universe expanded, the density of radiation and matter diluted. However, the energy density of dark energy remains constant, leading to its eventual dominance over all other components. This shift in dominance, from radiation to matter to dark energy, explains the universe's accelerating expansion. It's a cosmic changing of the guards, with dark energy now driving the show and shaping the ultimate destiny of all that exists. The study of these cosmic components, visible matter, and dark energy, is a continuous quest. New observatories, both ground-based and space-based, are constantly gathering data to refine our measurements and probe the nature of these enigmatic constituents. Ultimately, the universe's energy budget clearly demonstrates that space is not just filled with various forms of energy, but its largest, most mysterious component, dark energy, is intrinsically linked to space itself. This reinforces the idea of space as an active, energetic, and fundamental aspect of existence. Beyond our current understanding, theoretical physicists are exploring even more audacious ideas about the nature of space and energy. Theories like string theory propose that fundamental particles are not point-like, but tiny, vibrating strings of energy, existing in higher dimensions. String theory suggests that our observable universe might be just a brane, a higher dimensional membrane, floating within a larger, multidimensional space called the bulk. In such a scenario, energy could flow between these dimensions, manifesting in ways we cannot yet perceive. The concept of a multiverse, an infinite ensemble of universes, each perhaps with different physical laws and energy densities, arises from various theoretical frameworks. If true, the space we perceive might be just one tiny bubble in an unimaginably larger, energetic sea of universes. How energy manifests and behaves in these hypothetical extra dimensions is a profound question. It could explain why gravity appears so weak in our four dimensions if a significant portion of its energy leaks into other dimensions. The quest for a theory of everything, which seeks to unify general relativity with quantum mechanics, is ultimately a quest to understand the fundamental nature of space, time, matter, and energy at the deepest possible level. Its success would redefine our very perception of reality. Quantum gravity is a branch of theoretical physics attempting to describe gravity according to the principles of quantum mechanics. It explores a realm where space-time itself might become quantized, breaking down into discrete units at an unimaginably small scale. If space-time is quantized, then empty space would literally be made of energetic fluctuating loops or points. Its energy might be tied to these fundamental quanta, rather than being a continuous field. This would bring the concept of space even closer to that of pure energy at its most fundamental level. The holographic principle, an intriguing idea emerging from black hole thermodynamics and string theory, suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram. This implies that space itself might be an emergent property of underlying information. If space is emergent, what is it emerging from? Perhaps from a sea of fundamental information, or from pure energy fluctuating in a higher dimension. This shifts our question from "is space energy?" to "is space an emergent manifestation of fundamental information, or some ultimate energetic substratum?" The very existence of dimensions and their properties could be tied to the energy landscape of the universe. Some theories suggest that certain dimensions compactify curl up to an unobservable size due to specific energy configurations in the early universe, leaving us in our familiar three spatial dimensions plus time. These theoretical endeavors are not just philosophical musings. They are attempts to construct a coherent, consistent framework for understanding the universe's deepest secrets. They push the boundaries of what is conceivable, and in doing so, they continually redefine the nature of space and energy. The idea that space might be a fundamental entity or an emergent property is central to these debates. If emergent, then the ultimate reality from which it emerges could indeed be a form of pure energy, giving rise to all other phenomena, including space itself. This dynamic view implies that space is not just influenced by energy, but is intrinsically made of it, or gives rise to it. It moves us far beyond the idea of a passive void towards a universe where every point, every dimension, is infused with activity and potential. The journey to understand the fundamental nature of space and energy is far from over. Each new discovery, each theoretical breakthrough, pushes us further into realms of thought that challenge our intuitive grasp of reality, inviting us to imagine a cosmos more wondrous and complex than ever before. These theoretical constructs, although speculative, highlight the ultimate question. If everything, from matter to space-time itself, is ultimately a manifestation of energy, then in what sense can anything be truly empty? The universe, it seems, is a symphony of energy in countless forms. These profound understandings of space and energy are not confined to ivory towers or abstract equations. They profoundly affect our philosophical understanding of reality itself. They challenge our conventional perceptions and open new avenues for thinking about existence. The realization that empty space is anything but vacant, that it teems with virtual particles and is imbued with dark energy, fundamentally alters our place in the cosmos. We are not just floating in a void, but immersed in a dynamic, energetic medium. While direct technological applications from dark energy or quantum vacuum energy are highly speculative and far beyond our current capabilities, a deeper understanding of these fundamental forces could, theoretically, unlock future technologies. Imagine a future where we could harness the zero-point energy of the vacuum, a seemingly limitless reservoir of power. Or perhaps manipulate space-time itself for faster-than-light travel, though these remain firmly in the realm of science fiction. The limits of human perception are starkly evident when confronting concepts like dark energy and quantum foam. Our senses are tuned to a narrow band of reality, leaving the vast majority of cosmic phenomena beyond immediate apprehension. Science extends our senses exponentially. The scientific method, through observation, experimentation, and theoretical modeling, serves as our primary tool for navigating these abstract realms. It allows us to infer the existence of unseen forces and subtle phenomena that govern the universe. The beauty and mystery of the cosmos are amplified by these discoveries. The universe becomes not just a collection of objects, but a living, breathing entity, constantly evolving, expanding, and transforming, driven by its intrinsic, energetic nature. The ongoing search for answers to questions like what is dark energy, or how do quantum mechanics and general relativity unify, fuels scientific progress and inspires new generations of researchers. It's a testament to humanity's insatiable curiosity. Philosophical implications abound. If space is fundamentally energetic, then the very concept of nothingness is challenged. The universe might be a continuous outpouring of energy, manifesting in diverse forms, rather than a system slowly winding down from an initial burst. The role of observation and experimentation cannot be overstated. From the first telescopic observations to sophisticated particle accelerators and gravitational wave detectors, each technological leap opens a new window into the universe's energetic secrets. Understanding the energetic nature of space also informs our search for extraterrestrial life. The conditions and energy distributions in different parts of the universe play a crucial role in the potential for habitability and the emergence of complex life. This journey of discovery allows us to contemplate how our own existence is intricately woven into the cosmic fabric. We are, quite literally, made of stardust, and our physical reality is deeply connected to the energetic properties of space itself. The evolution of our scientific models, from classical to relativistic to quantum, highlights a constant refinement of understanding, revealing layers of complexity hidden beneath simpler appearances. Each layer reveals a more energetic, more dynamic universe. The pursuit of these cosmic truths is not just for scientists. It is a shared human endeavor that expands our collective consciousness and our appreciation for the astonishing reality in which we exist. It is a story of continuous unveiling. Ultimately, the question, is space pure energy, leads us to a fascinating conclusion. While not entirely pure energy, space is undeniably active, energetic, and a fundamental participant in the universe's every process. It is infused with potential, driving the cosmos forward. In summary, our journey through the cosmos has revealed that the classical notion of space as an empty, inert void is fundamentally incorrect. Modern physics has painted a picture of a universe where space is a vibrant, active, and energetic entity. We began with the understanding that energy is the capacity to do work, manifesting in many forms, and that Albert Einstein's E=mc² showed mass itself to be a form of concentrated energy. This blurred the lines between matter and the energy that permeates everything. Quantum mechanics unveiled the quantum vacuum, a realm of constant activity where virtual particles flicker into existence from seemingly nothingness, leaving behind an irreducible zero-point energy. The Casimir effect provided tangible evidence of this vacuum energy. On the largest scales, the accelerating expansion of the universe revealed the dominance of dark energy, a mysterious, uniformly distributed energy property of space itself. Current models describe it as a re-emergent cosmological constant. General relativity linked space and time into spacetime, a flexible fabric warped by mass and energy. Gravity became a manifestation of this curvature, and gravitational waves proved spacetime's dynamic, energetic nature as ripples flowing through it. The universe's energy budget, dominated by dark energy, confirms that what we perceive as nothing is actually the most prevalent and influential component of our cosmos, dictating its large-scale structure and ultimate fate. Theoretical physics continues to explore even more exotic possibilities, from string theory's vibrating energy strings in higher dimensions to quantum gravity's granular spacetime, and the holographic principle hinting at space as an emergent property of information or energy. These profound insights have not only expanded our knowledge, but have also deepened our wonder, compelling us to ask ever more intricate questions about the fundamental nature of existence and our place within this energetic universe. So, is space pure energy? The answer is nuanced. While not solely pure energy in any single simple form, space is undeniably imbued with energetic properties at every scale. It interacts with energy, it carries energy, and its very geometry is determined by energy. From the flickering of virtual particles in the quantum vacuum to the expansive pressure of dark energy dominating the cosmos, space is far from a passive stage. It is an active, energetic participant in the grand drama of the universe. The universe is a continuous process of transformation, where energy manifests as matter, matter reverts to energy, and space itself expands, stretches, and curves under the influence of its energetic content. This profound connection between all cosmic elements, matter, energy, space, and time, points towards a unified reality, where distinctions blur and everything is interconnected at a fundamental level. The enduring mystery, however, remains. While we understand much about the manifestations of energy in space, the ultimate nature of dark energy and the reconciliation of quantum mechanics with gravity continue to elude us. Yet, it is in this mystery that the true wonder lies. The boundaries of our knowledge are constantly expanding, and with each discovery, our appreciation for the sheer elegance and complexity of the universe grows exponentially. The question, is space pure energy, invites us not to a simple yes or no, but to a deeper understanding of a universe where space is a dynamic, energetic entity, profoundly connected to everything that exists within it, and continues to hold vast, exciting secrets. This evolving view of space directly impacts our fundamental models of cosmology. From the Big Bang's earliest moments, where space itself began expanding, to its accelerating future, every epoch is characterized by specific energy dynamics within space. The energy of space, particularly its expansion, literally defines the observable universe. The cosmic horizon, representing the farthest visible edges, is a direct consequence of how fast space has expanded and how long light has had to travel to reach us. Consider the implications for potential cosmic engineering or manipulation. If space possesses intrinsic energy, could future civilizations theoretically tap into it, or even sculpt space-time in ways we can barely conceive, leveraging its inherent energetic properties? This understanding also influences our theories about the very beginning of the universe. Models of cosmic inflation, for instance, propose that the very early universe underwent a period of extraordinarily rapid expansion driven by a different kind of vacuum energy. Ultimately, the more we learn, the less empty space becomes. It's a fundamental component of reality, brimming with potential, constantly influencing and being influenced by everything within the cosmos. Space is not just where things happen. It is a fundamental part of what is happening.